So I'm getting again sidetracked. Today I stumbled upon this beautiful Twitter thread, which kind of I'm surprised because it seems the tweet was from May 24th, 2019, right? And the original tweet from Michael Nielsen. Then I think the reason I stumbled upon this is because basically, where's the I hate the way this works. I mean, Grant Sanderson basically replied to these kind of today, and then Craig replied to this. I think that's the reason. Oh wait, so Craig replied by then as well. That's a measurement based on computation. If a qubit qsat is computationally basis function of other qubits R, you can get rid of Q by measuring it in the X basis and using the result to control phasing operations on R. Useful tool. Okay. What I'm here to try to do is try to kind of I want to try to basically start a series on building intuition around the question that Michael asks at the end of the thread, where he's basically kind of reducing the teleportation circuit in a way that he kind of says that you because of the symmetry in here, you can just move the control knot to the other wire. And then he kind of goes ahead and then, gets rid of the wire. Well, I mean, it's really fairly simply explained in the thread. So go ahead and read through these. And then at the end, he's like, once you've got the circuit, like, yeah, you can do the algebra and then go through the stuff and see that it works. But he kind of like was looking for a way to explain why is it that you end up with something like these, right? Where what you have is you have a at the end, like in this system in here, you kind of have these two states where it's like if you measure the qubit, the top wire to be 0, you got to do nothing. If you measure the top wire to be 1, then you got to correct the state. So you got to correct the state just by the phase, by this phase in here, right? Quickly, the way this looks like in Quirk, if you do this, right, is so if you just let's say imagine that the state that want to teletransport is this one. Teleport is this one exactly. So the one that you see in here, right? Like, make that clear, and then you do a control knot and a Hadamard gate, and you take a look at that state in here. You see that basically, I mean, if I make that bigger, because now it's a 2-qubit system, so it doesn't make so much sense to take a look at just the wire. You see that this state, that's an awful color that I chose here, this state is now encoded here. Right, so basically what this means is that if you how can I do this? If you measure the state to be 0, so I'm going to use the postulate gate, you actually get the state that you want teleported to the bottom qubit, because that's the bottom qubit, right? Bottom qubit. Yeah, okay, because the phase is global, like, because the phase is relative, that's correct, right? Like, it's the same, this is physically equivalent to these. Yeah, that's exactly. So you get the state in here. Whereas if you pause select for 1, you get kind of the same, like, you just have to apply a correction, right? Which is basically a Z gate here to get what you want. So that's it, right? Or the way this is explained in here is, there's the little exponent in here, meaning if you measure a 0, then it's going to be a Z to the power of 0, so the identity, or if it's a 1, it's Z to the power of 1, so that's the Z gate. And And so why is that, right? Like why, if you do the algebra, then you see that it works, and but there's no clear intuition for these, right? Like there's some nice notes that then uh, that are then made like by Grant in here in terms of like, and it's funny because this is really indeed it's a really similar representation to what Quirk is using. I think the only difference is the columns, and it seems to be a transposed version of these. Um, and so Grant talks about like smooshing and sort of the smooshing effect that the Hadamard has and stuff like that. And the only reason that I found it fascinating because this is basically the very exact reason why I started the channel. That like if you see stuff like that, you just take a look at an algorithm, a quantum algorithm. Yeah, you can do the algebra, and then you see that it works, but it doesn't explain you in an intuitive way why it works, right? Like, and that kind of makes it like it, to me, it makes me feel like I'm left at the mercy of the maths, and so I got to trust the math, and which kind of makes sense. You should trust math, obviously, but it somehow makes things a bit like it makes me feel weirdly uncomfortable that I just can't intuitively understand something, and I have to rely on just a series of formalisms to lay out that something really works. Um, but it's just a matter of taste, I guess. So what I wanted to do in this series is I wanted to basically, and it's going to take a bit because I'm not sure myself of whether my ideas are here correct or not. So that's going to be really quantum intuition style. We're going to be trying to build that up and build the intuition up together from scratch, and so you kind of get to see the journey as well. So it's not that I have a solution ready in my hand. I'm just going to drop it in here, and then um, yeah, and then there you go, right? So that's the point. So the first, yeah. So I'm trying to think how to approach the problem, right? Like for me, what I would expect is in a similar way what that I did with Grover's algorithm, where I really wanted to understand what each system level gate is doing, and by taking a look at it from an interference perspective, we learned that what the amplitude amplification is doing is kind of applying a phase correction tweak so that you get the interference effects that you want for Grover to work. So I want to do something similar in here. And I mean, where do we start? Well, like for me, the most or the trickiest point in here is to kind of let's just get rid of all these, right? Like let's go to kind of a more basic form of these, because what. And I'm liking this because I really want to try to approach that from interference, and then entanglement is a component of it as well. And so that's kind of that's it's good because it's going to force me to think about these in a way that I haven't before. That I haven't really thought about entanglement in a more intuitive way. And so let's just assume, like, I like that state as an initial state, or as a state to teleport, but we can then play with other ones as well. I just don't. We could try playing with something more simpler, but I'm afraid that if I use a Hadamard, we're going to get some interference patterns because of the pluses and minuses that are going to just hide some of the actual intuition behind these. So maybe we should just go ahead with these, which is not that straightforward. Sorry, go back to 0. Yeah. And so kind of what I want to understand first is really what the entanglement is doing. I shouldn't maybe call it entanglement, but like what the control NOT gate is doing here. It is indeed creating entanglement, but the gate doesn't always create entanglement. That's kind of step number 1. And step number 2 for me would be to understand what it means. So maybe I should start from state number 2, because I'm not feeling super sharp with entanglement right now. But step number 2 would be to understand what is the intuition of applying a Hadamard gate to just a subsystem, right? Like if here my system is 2 qubits, and so I'm just applying a Hadamard gate in one. Because if we go back to, let's assume we just have one wire, right? Like I always like to see the Hadamard gate as a, if I just focus on the non-superposed states, right? Like just the 0 or the 1. What the Hadamard gate does is really encodes these into the phases of a superposition, right? So the 0 state translates into a state where the two phases are equal, and the state 1 translates into a state where the two phases are, the relative phase is 180 degrees, right? And so this is, because information can't be lost. That's the key. Because if we then uncompute, then we kind of go back to the initial state. That's what we want to do. Now, the same applies to 2-qubit system when I apply like a Hadamard layer to all the qubits, right? So if I have like the state, the state like 0, 0, this Hadamard layer in here is kind of doing this encoding, right? Like this encoding of these into that different bases, right? Like you in this case, it's encoding each possible state into a different combination of the phases. So pay attention. 0, 0 equals to all the phases are, there's no phase in there in the system. 0, 1, it's phasing the state 0, 1 and the state 1, 1 by 180 degrees relative to the 0, 0. The state 1, 1 is phasing the 0, 1 and the 1, 0, etc. Right? So it's always a unique combination, because if you apply if you uncompute these with another Hadamard layer, you kind of should go back to the original state. And remember, what's happening here in between is interference. It's destructive interference. So we've seen this in the 30 plus videos of Grover's algorithm. But what's the intuition behind applying just one Hadamard, right, to a subsystem? That's what I'm kind of not like really super familiar with. Where I don't have a sort of an understanding of what it means, right? Like if I just either choose a portion of, and I'm not even thinking about a 3-qubit system, because that is okay. Let's stick to 2 qubits for the moment. Because what it's doing is, so the 0, 0 is encoded into like that superposition. So not only it's the phase, because this state, it's also the phase that's changing. Okay. And this state, it's funny because it somehow feels like a one Hadamard alone is enough to have a good mapping into this other 2-qubit system, because it's mapping all the information there is uniquely. Okay, no, it's yeah, it is, because it's got more space, right? So here we have again the two phases. Okay, so the way this works is this type of mapping doesn't map everything. Okay, so it just maps the wire where the Hadamard is being applied into the phases, and the other wire is basically kind of where the amplitudes exist, right? Like there's no amplitudes in the 0 portion of the whole system. Whereas if it's like a 0, right, like it stays here. Okay, cool. So these let's put it this way, this wire is encoded into what half of the system we're going to be using, and this wire is encoded into the relative phases of that half. Now, what happens with a, and so how can we extend that to 3 qubits, but still keeping just one Hadamard? It's the same, right? So these two wires basically, sorry, there should be a way to, there's no way that I can go back to 0. I gotta rotate it. Okay, so I should probably use the next gate. I'll just have a spare one here. Oh yeah, but then that kind of shouldn't matter. Okay, so that only kind of moves. So these 2 qubits are encoded in the space, in the correct portion of the the actual system's possible states, and then it's only this one that it's encoded in the phases. Okay, so what this is saying is that when you, so you're kind of, you could think of these as encoding the wire into the phases, right? And the other two don't go there. What if I have 2 Hadamards? Okay, so that's kind of the same. You pick what, pick what portion you want to use, and the other combination is mapped into the phases of that subsystem. Okay. It's a bit of a hybrid mapping, right? Like, but but I don't think that's taking me anywhere. Let's go back to these. What about so what about superposed inputs, right? Do I have an intuition about these? I think I don't, because it involves interference. So what if I say, I mean, that is obvious, right? But like, what if I have trickier things like these? Okay. So if I have this state and I apply a layer of Hadamards in here, that's the output state that I have. And I should probably do this by hand. Kind of take a look at what type of interference is going on in here that turns these into that, and see if there's a pattern to these. Okay, because then I see that when I remove one of the Hadamards, then there's going to be another interpretation of that as well. I wonder if it would be a mixture of an interpretation like we're sort of encoding something that's got to do with this wire into the phases versus this wire what? Versus the state of this wire being where? Right, like encoded. Because now we've got all the space used already. I know this might seem like I'm going far away from, but like, let me go back to the whole thing here. So what we're trying to do is, what the hell is this? So what I'm trying to do is I'm trying to basically, get us to understand and build intuition on what's going on here, right? Why are we getting this state in here without actually doing the algebra, right? Like, and trying to kind of, for me, this has 2 steps. This is one of the moments, and this is another one of the moments. Even though there's no gate in here, I kind of treat these as a system-wide operation. That's what I want to try and understand, is what does this type of operation mean at a system level, intuitively? Mm, and that's what I'm kind of trying to understand now, right? So I'm probably going to be calling these videos somehow like partial Hadamard layers or something like this. Um, it probably has an official name, but I don't know. Good. So how do we do this? Do we open the notebook, the notepad? Probably open the notepad just because I could use the pen, but I want to remember these. And can I zoom? Yeah, I can. I can do these, right? So let me see. What is the state that we have here, right? So we've got like a 0.5 real and a 0.5 imaginary, 0.5 imaginary and like minus 0.5 real. So we've got like our system, right, is in this state, and I'm gonna ignore. I'm gonna ignore. I'm not gonna normalize stuff unless I really need to, because it just that was imaginary, right? And then this is also imaginary, and then this um, was minus 0.5, right? Like real. Was it? Yeah. Okay. Just to keep the things aligned, I'll keep the pluses in here. So now let's say we apply the Hadamard like to Quirk is using the top qubit is the rightmost qubit in here. So this is going to be after the Hadamard is applied only to that qubit. We're going to take a look at how this evolves, and here we get like obviously 0.5 plus 0.5 real 0 plus 0.5 real 0 1. So all we're doing is we're applying something that we a second, can I just not just do these probably? Yeah, that's about it. That's good. So all we're doing is we're applying. Oh, I can't draw in there. Come on. So we're applying the Hadamard to. Sorry, guys. Here we go. So I just apparently can only draw in here. So we're applying the Hadamard in here, right? So Hadamard 0 is 0 plus 1, and that's kind of why this translates to these. And what we're gonna get in here is basically, I can copy these and say that basically what this is gonna give us is, it's gonna have a minus in here because the starting number is a 1, right? Whereas in here we're gonna have this, and we're gonna have these. Yeah, and here we're gonna have minus that stays here, and this minus turns into plus. Okay, this is just because the Hadamard on here would lead a minus, and minus times minus is plus, and so that's why I get a plus in here and a minus in here. Okay, so what have we done now? So this is applying sort of a partial Hadamard layer on this qubit, on this wire, and that should somewhat lead me to these, right? Okay, I see that here we got like 0.35, and this is because it's normalized. Is 0.35? I guess so. I guess that's the reason. I'm gonna assume that. So I don't want these. So what do we see here is the 0 0 component So we see here there's no destructive interference in the sense that there's no term being cancelled out. And there's no term being cancelled out, but the phases seem to have some yeah, well, they actually suffer some effect, right? Like my question here would be, is there a way to get destructive interference other than like what if we would get into the plus state in here, and I know there's destructive interference, and now we would apply the spinning gates. So let's spin these guys. Even if we just spin this one, there is already some interference, right? Because the amplitudes are changing as well. Okay, so it actually feels like the only moment where there's no interference is really when you've got those phases, sort of either you've got like an 90 degrees, or like minus 90 degrees. The reason being that, why is that? Let's tweak that a little bit. Let's say I want to move the 0, 1. 0, 1, so that would be, I want to move this phase by, not ST, for example. Okay, so here we've moved this guy. And what if we do the same here? Sorry, I want. Okay, so now I shifted in here. So I shifted these two a bit. I moved them a little bit, and now I'm seeing some destructive interference. Why is that? Why is that? Okay, because we've got here both. Okay, the reason is because we've got here both real and complex. That's why. So it seems from these I can take intuitively, if you okay, but here it doesn't happen, right? Like, that's interesting. So for partial, what I can say is that for partial Hadamard layers, the only way to get destructive interference is when some of the phases, like when at least one of the phases has got both a real and an imaginary component. The reason being that then things can cancel out, because if can they? Let's take a look at this. I mean, let's make one simple example. Well, just move one. Okay, so I'll just do these. So we just have to redo a portion up here. So this is the 0, 1 case where we said we have, so everything else is as we had it before, and this is minus 0.35 real. Did I say minus? Yeah, and plus 0.35 imaginary. So how do I do the math on these? So this will obviously translate into these, right? Can I just say, or is this like a scene? Can I just turn these into, let me copy the whole thing. Can I just turn the whole thing into like, yeah, probably. I can probably do that, right? I can probably do that, yeah. That's the reason that we've got some interference. Because now we've got these element and this element, they are partially canceling out. And if you pay attention, it's everything, it's attacking the 0, 0. So the intuition here will be, I mean, there's definitely something interesting that it seems that the elements that don't have, I don't know how to call them, like purely complex or purely real components, are the ones that suffer. And at the same time, no. It's not true. They actually don't suffer. They suck up amplitude. And they suck it up from the element that kind of would generate, because these partial Hadamard layer on 0, 1 would generate 0, 0, and 0, 1, right? But negatively. They suck amplitude, and the faces just get all just messy. That's complicated. Like, how can we build any intuition out of these? That is actually complicated. What if it's this one? And it behaves differently. So what I just said is wrong. No, it's not wrong. Okay, so it does take, that element does eat up some amplitude, so it gets fatter, and then this element, which is sort of the partner element from a partial Hadamard layer perspective. So the structure of these will affect which one is it sucking from. Yeah. So he's sucking from 1, 1. He's sucking from like 0, 0. I should have probably used these words, but that's the way this looks like. This looks like, I don't know what I just said. So I could say that it's when elements have like mixed real and complex that we see interference. And to be honest, well, I just actually proved myself wrong. What? I proved myself wrong totally. Here we have amplitude. Here we have elements where, yeah, we have amplitudes where. Wait a second. This is weird. -0. That could be. What does it even mean, -0? Okay. That could be the reason. But it's not, because this is the one that's gaining, but it doesn't have the mixture that I talked about. Okay, so that makes no... It proves me wrong, maybe in the sense that it's not the only case where we observe destructive interference, but for sure, when we've got like non... No, okay, but it's also not true the way I put it here. So okay, so you can't easily... there's no simple intuition, I think, in terms of which element eats up what. It's got to be either the one that the one that's kind of off from a phase perspective, or the one that's kind of like the partner from partial Hadamard layer perspective. Okay. So these are the types of interference patterns that we're generating. Where does this take me, though? Like, I think I'm really far away from these still, right? Because here we have a system where we've got like a... oh, where's my pen? Here. Where we've got like... because I can of course, with the visualization, I can easily say, oh yeah, the state, like, look at these, the state is encoded into the diagonal, really, right? Like, if I do this, like, the state is encoded in the diagonal, and the only thing the Hadamard is doing is kind of replicating these elements into their other squares. Of course, this one kind of gets like the opposite, like gets kicked back, like this face gets kicked back, like opposite. And yeah, but that's not the point. That's not what I'm trying to understand. I'm trying to understand, or I'm trying to find a way to talk about this circuit intuitively, and maybe from an entanglement, purely entanglement and interference, sort of at that level of abstraction. It kind of feels like what this feels like is there's actually some creative... so what it seems like is there's some creative interference in here going on, because it's a state that it's entangled. That's the wrong thing to say, though. Because that is still entangled, right? Yeah. And there's a bunch of weird things going on here. But there's something about that particular state that makes it prone to creative interference. And maybe that's a way to think about it. At the end of the day, the Hadamard layers either, like, they superpose stuff, right? Like, but this superposition effect can have the side effect of, creative or destructive interference. Is it creative the right word? Like, whatever. They add up, right? Like the maybe let's do this. So we've got like a 0.85 real, 0 plus 0.35 in complex. And we've also got a 0.1 plus 0.15 real for 1, right? Minus 35, okay. Minus 35. So, and so when I apply a Hadamard, yeah, that's actually going to create. It's going to create stuff, right? It is no real. It's not really. No. This is not creative interference. This is just superposing stuff. So you're superposing an entangled state because these turns into, well, let's just like, the following system. Like this turns into, these plus these. I mean, normalized, right? Like, so I'm cheating here. Okay. 0.60 and 0.25. There's no way I would know that intuitively, I think, but I know it's kind of creating these. Wait a second. Yeah. Yeah, no. Okay, sorry. It's doing these. So it's creating these state, like 0.85 kind of gets, so 0.85, 0.35, it's like 0.60, 0.25, but then it creates these. So this is new information. I don't know if it's correct to say this is new information. And these guys, 0.10 and 0.25. Minus 0.10. And what did I say here? Minus and plus. And this is plus. So there's no interference in here. There would be if I would apply a full Hadamard layer. But there's no, I mean, here I can see that there's just no, because there's simply no amplitude for the state 0, 1, right? Well, the amplitude is 0. And so we're kind of filling this up. And now we really have, the thing is that it's not that obvious. It's not that obvious that this state is the state encoded in here, because the actual amplitude is spread like across the other part of the state as well. So it's only when we measure 0 that we get the things here, kind of adding up and then renormalizing. So literally would be that if we sorry, and this is that's wrong. So this is so this would kind of mean that we're taking these part and this part of the system. That's the only thing that we're doing, right? So we're not taking these parts of the system. And so so this is redundant, right? So these things kind of then renormalize and we go back to these state. That's all we had. But why? I'm still not really gonna leave it here for the first video. I'm still not really sure I'm onto the right path. So what was Craig saying other than that? So Craig is saying that's a measurement based on computation. If a qubit q is a computational basis function, is a computational basis function of other qubits R. You can get rid of q by measuring it in the x basis and using the result to control phasing operations in R. Useful tool, see the appendix C. What do we got here? Whoa. Qubitization of arbitrary basis quantum chemistry leveraging sparsity and low rank factorization. That's beautiful. That's insane. I'm never going to be able to read this. There's some appendix C apparently. I can't really. Oh, F. C, D. There's some interesting stuff in here, I think. Efficient uncomputation of table lookups using measurement-based uncomputation. Okay, so measurement-based uncomputation, this seems to be... Yeah, well, that's kind of desentangling, right? Like, that's what you want to say here. So you kind of can control... on 0. No. Okay, that will be not the case. So the case would be, yeah, but that's what pulse selection is doing, right? So there you go. You have the state in here. So we're pulse selecting for one, and then so the measurement is uncomputing. Is it? Okay, but still, that's kind of one step ahead of. I think I'm jumping one step ahead of the game here. And computing a table lookup using eager measurement and phase fix-ups reduces the effective address size from D to D divided by 2 and the effective output size from M to 2. So there's a lookup. Interesting. And this is gold, probably. Yeah, I don't know. Oh man, what did I just start? Um, okay, I'm gonna figure this out. I'm really gonna figure this out. Um, where did I? So just to sum it up, basically, what I'm trying to understand is I'm trying to understand, sort of, have a first principle understanding of what a partial Hadamard layer is doing intuitively. Um, how could I think about it differently, right? Mm, to be able to apply these kind of interpretation here, and rather than just saying, okay, I see the boxes moving and whatnot, like, and this is what we need to build up for like proper quantum intuition. Because I think that's going to be really at the higher levels what it's gonna help us build actual understanding of what like entanglement is as a resource and stuff like that. I don't know. Mm, kind of feel like this is the so that would be what, yeah, you're entangling these, right? So you're spreading the state across, and then it's like I understand it, but I'm not happy with what I understand. That's the problem. Because, okay, the Hadamard, the partial Hadamard in here, maybe there's no way to generalize that, but like the partial Hadamard in here is superposing. It's actually helping me superpose. It's really superposing an entangled state. That's all it's doing. It's superposing an entangled state. What does it mean to superpose an entangled state? Maybe that's a question that I should try to answer intuitively. What does it mean to superpose an entangled state? It's kind of like would an entangled system or whatever state. It's like, can you ask yourself, what does it mean to superpose a superposition, right? Like, um, is there a difference between these two? What does it mean to superpose an entangled state? Is there any way to define what it means to superpose an entangled state? Yeah, I guess that's kind of a way to think about it. So, does it mean to superpose? Can't see what I'm reading. An entangled state. So basically, I'm going to call these interpretation stuff. Kind of revisiting teleportation in this sense. So what does it mean to superpose an entangled state? We understand what it means to superpose a non-superposed state, right? Like, and superposing a superposed state can create interference and can take you back to either another superposed type of state. And but it's like I feel there's no simple way to understand the effects of Hadamard layers in an intuitive way, other than I kind of like the piece of, okay, if some of the phases are have a mixture of complex and real components, um, then you're going to get some destructive interference. There's a clear pattern in there. It's not a general thing in terms of only. It's it's not a unique property of these types of input states, but it's definitely a pattern there. Mm, yeah, good. It's been a complicated hour, as with these things, but it's just the beginning. So yeah, looking forward to dig into this more. Cool.